In other words, m and n and x are all elements of R now. This is a substantial advance into all kinds of possibilities. We are no longer restricted to the exponent being a natural number in the work that follows. This means that exponents can be zero, positive or negative counting numbers, and even fractions or decimals. Any real number, whatever. For example, doing the multiplication of powers again, this is the case where powers of the same base are multiplied and exponents are added. X to the fifth multiplied by x to the negative 9. Add the integers, and the result is x to the negative 4. Another example, x to the 1/2 multiplied by x to the 1/2. This is equal to x to the 1/2 plus 1/2, and that's equal to x to the 1, or 1 understood. Another example, x to the 1/2, x to the 7/3 is equal to x to the 1/2 plus 7/3. Adding these fractions will result in 3 plus 14 over the common denominator 6. The final result, when simplified, is x to the 17/6. Continuing with more examples, let's look at the division of powers. In this application, when the bases are the same, the exponents are subtracted. For example, negative x to the 12th divided by x to the negative 5. Exponents here are integers. This is equal to negative x to the 12th subtract the integer negative 5. So this is then equal to negative x to the 12th plus 5, which finally reduces to x to the 17th. Another example, a to the negative 5 over a to the negative 6. Again, a to the negative 5 subtract the integer negative 6, other into a single positive sign, and we have an x to the negative 5 plus 6, which finally equals a to the 1, or 1 understood. Another example, a to the 7th divided by a to the 7th. This is equal to a to the 7 minus 7, which eventually is expressed. We conclude that a to the 0 is 1 also. The next example will deal with the power of a power. For example, 4 times 10 to the negative 2 to the 6th is equal to 4 to the 6th times 10 to the negative 2 times 6. This reduces to 4,096 times 10 to the negative 12. This is equal to 4.096 times 10 to the third times 10 to the minus 12. And finally, I can express this in the following fashion: 4.096 times 10 to the negative 9. Another example, 2ac to the negative 2 raised further to the exponent 3. This is equal to 2 to the third, a to the third, followed by c to the minus 6. Simplifying the numerical part of the expression, we have 8a cubed c to the minus 6. Another example, 4a to the sixth, c to the minus 3, to the 1/2. This is equal to 4 to the 1/2, followed by a to the third, and finally c to the minus 3/2. I'll write it here, 2a to the third, c to the minus 3/2. Another example, 12 y to the minus 2, z to the fourth, over 3y z squared. I need a larger bracket there. All of this raised to the second. 4y, subtract negative 2 and 1. Negative 2 subtract 1 is y to the negative 3. Subtract 4 and 2, the answer is 2, all raised to the second. We can now apply this outside exponent, simplifying 4 squared is 16, y to the minus 3 squared is y to the minus 6, z squared again is z to the fourth. Although you have all the rules you need to work with exponents, there are a few more rules which are so unique or special that it is worth discussing them separately. You have already seen the following rule before as an example earlier, and it will be repeated now for emphasis. The zero or null exponent. X to the 0 is equal to 1. X must never equal 0 itself. Memorize this rule. This is true for all values of x, except, as I explained, when x is equal to 0. 0 to the 0 is undefined. You might want to try this on your calculator. Put in the number 1,000,000. Use the power function key, enter 0, and work out. Another example, try it on a very small number, something like this, and you will find that once again the calculator will display the number 1. So in the work on this chapter, you might be given questions such as 4 multiplied by 3x to the 0 multiplied by y third to the 0, and asked to simplify. We have a 4. The x to the 0 here is 1, and so this part in brackets is equivalent to 3 times 1, or simply 3. Y cubed to the 0 is simply 1 again. And 4 times 3 then reduces to 12. The proof of this rule is fairly simple. Given x to the m divided by x to the m again, by the rule of division of powers, that is equal to x to the m subtract m, which in turn is x to the 0. But by the rule of simple fractions, where you have the same expression in the numerator as you have in the denominator, the entire fraction can be replaced with a 1. So this is equal to 1. And consequently, the conclusion is that 1 is equal to x to the 0. The next special rule, Rule 5, we'll refer to as the reciprocal rule, or the rule of negative exponents. X to the negative m is equal to 1 over x to the positive m, or 1 over x to the negative m is equal to x to the positive m. Memorize this rule. The rule can be shown to work by using a specific example, and this method of proof is often called proof by example. By using the rule of division of powers in the following: x to the 5th divided by x to the 8th, we have that this is x to the 5 subtract 8 equals x to the minus 3. If on the left-hand side of this equation I write x to the 5th as a continuous multiplication of 5 x's, and below in the fraction as a continuous multiplication of 8 x's. That leaves 1 in the numerator and x to the 3rd in the 1 over x to the 3rd is equal to x to the minus 3. The last special rule of exponents is one which involves fractions for exponents, and this has already been hinted at in one of the examples earlier, and I'm going to repeat that example now. The example we dealt with was x to the 1/2 multiplied by x to the 1/2 is equal to x to the 1/2 plus 1/2, which equals x to the 1, or 1 understood. Another similar example is if I take 4 to the 1/2, multiply it by 4 to the 1/2. This is 4 to the 1/2 plus 1/2, or 4 to the 1, or simply 4. Let's examine the left side of this last example. You can see that I have multiplied a number, 4 to the 1/2, by itself. another 4 to the 1/2. For now, I'm going to ask this question. What number, in place of 4 to the 1/2, multiplied by itself, will give me 4 as the answer on the right? 2 times 2 is equal to 4. By making a comparison between the same two things that result in 4, we can conclude that 4 to the 1/2 must be an expression that is equal to 2. But we also know an additional fact regarding 4, in that the square root of it is 2. The conclusion is then that 4 to the 1/2 must also be the same as the square root of 4. The interpretation of this fraction is that it is the square root of 4 as a radical. In general, therefore, x to the 1/2 can be interpreted as a radical expression, that is the square root of x. Similarly, we can show by going through the same kind of argument that if we take 27 to the 1/3, that is the same as the cube root of 27, which equals 3. Consequently, x to the 1/3 in general terms is equal to the cube root of x. And so on. Even more generally, x to the fraction 1 over n is equal to the nth root of x, where n in this case is the denominator of the fractional exponent, and n is strictly a natural number. By emphasizing the word strictly here, we mean that it can only be a natural number and none others. Another commonly used name for this denominator n, when it is written within the radical sign as I have here on the right, is the index. N is the index of the radical. This results in our Rule 6, fractional exponents. X m over n, x to the m over n, is equal to the nth root of x to the m. N, comma, m are natural numbers. Of course, x is any real number. Or x to the m over n is equal to the nth root of x, all of which is raised to the mth. Memorize these results. Now we will do some examples. If the root of the base x can be determined as a simple integer, the best choice between these two results is the one which involves the least amount of work, and it'll usually be the second choice. For example, 8 to the 2/3 is equal to either the cube root of 8 squared, which is this interpretation, or it can be written as the cube root of 8 quantity squared, as indicated by this alternative. This is equal to the cube root of 64. And the cube root of 64 is equal to 4. On the other hand, if you took the cube root of 8 first, which is 2, and then squared it, the result is again 4. But in the second choice, the work is simpler. Here are some more examples. 32 to the 1/5 is equal to the 5th root of 32, and that is equal to 2. Another example, negative 32 to the 1/5 is equal to negative the 5th root of 32, and that's equal to negative 2. Another example, enclose the negative sign within the brackets. This is then the 5th root of negative 32, and that is negative 2. Compare these results and see that they are different, even though the final answers are the same. Another example, negative 4 to the 1/2 is equal to negative the square root of 4, and that is negative 2. Another example, negative 4 to the 1/2 is equal to the square root of negative 4, and there is no solution here. There is no real root for negative 4. This shows an important property regarding roots of a number. If the index is odd, such as it is here, 5 is an odd number, and the number underneath the radical is positive or negative, an answer can be determined. But if the index is even, such as in these examples, then an answer is possible only if the number under the radical sign is positive. When the base is a number, these are bases that are numbers. It is commonly simplified in the manner I've just described. But when the base is a variable, it is best to leave the exponent as a fraction. Consequently, it is of no benefit to change x to the 1/2 to the square root of x, for example.